Welcome to this web lecture on Hamiltonian cycles. So in this first video, I'm going to walk you through what Hamiltonian cycles are, and then we're going to have 3 follow-up videos where we're going to use the concept of Hamiltonian cycles in a transport context, in particular to find a route where we visited multiple customers. So the example that we're going to look at is the example of the Miller family. And the Miller kids, Alice, Bob, and Chloe, would like to visit the zoo, and in particular they all came up with some animals that they would like to visit. So for example, Alice would like to visit the monkeys, the elephants, and the giraffes, while Bob would like to visit the lions, the goats, and the butterflies. So now the Miller parents, good parents as they are, say, okay, we're going to try to come up with a route that is feasible on that day, that we can still be back to the entrance on time, where we don't see things twice. But we're trying to visit all of these 9 elements that the Miller kids mentioned. So the Miller family is asking multiple different questions. How can they visit all animals exactly once? How many different tours exist such that the Miller family visits each animal exactly once? What is the shortest tour to visit all animals exactly once, and how can the Miller family prioritize one animal over the other in case visiting all 9 animals is not feasible? And in this video, we're going to look into the first 2 questions. So we're going to figure out when such a route exists, how such a route looks like, and we're also going to look at how many of those routes exist. And the underlying concept, as already promised in the beginning, is the Hamiltonian cycle. A Hamiltonian cycle is a closed cycle which contains all nodes in a graph exactly once. Closed cycle means we're starting somewhere, we're ending there, and of course we're continuously moving forward, so we're not jumping, etc. And against this concept of Hamiltonian cycles, there's multiple questions that need answering. So first of all, does such a cycle always exist? And looking at the second question, the answer is most likely no, because we can also ask, when does such a cycle exist? We can ask how many Hamiltonian cycles exist in a graph. And for all of that, we're now going to look into multiple different examples. So the first example is this graph. And this graph does not have a Hamiltonian cycle. And the reasoning for that is rather simple. So if we look at those nodes here at the bottom, if we wanted to visit this node, we would somehow have to get out of this segment down here back to the graph on top. And that is impossible here. So we would have to use the same edge, which goes to the left twice, which also means we have to traverse the arc left of the one with an in-degree of 1 twice. So that is impossible. The second graph we can look at is this one. So here we have one additional edge. And this edge actually makes it possible for us to find a Hamiltonian cycle, and in particular this Hamiltonian cycle that you can see here on this slide. And this graph only has one Hamiltonian cycle, and the argument behind this is, if you look once again at this segment down here, this segment, so we have to traverse this segment entirely to even connect those 2 nodes here at the bottom, which both only have an in-degree of 1. The same actually also holds for these nodes here, so we also have to traverse this segment like this. And if we then already have these 2 segments where we already know how we have to traverse them, then the only question is how we connect this node, and this is then fairly obvious, and there's only one option. Of course, if we add 2 additional edges, we might end up with a lot more Hamiltonian cycles. And what I would like to ask you to do is to figure out all Hamiltonian cycles which exist in this graph. So this is the first graph. We also have a second graph, so this is known as a full graph. And for this, the question is the same. How many Hamiltonian cycles exist in here, and which ones are they? So if we go back to the 3 questions that we were asking in the beginning, does such a cycle always exist? When does such a cycle exist? And how many such cycles exist? We can at least partially answer them at this point. So for the first question, no. There is cases where no such cycle exists. One case could be disconnected graphs. Secondly, if we're asking when does such a cycle exist, this is non-trivial to determine. Of course, we have some rules, as for example, if it's disconnected, it doesn't have one. But we can also look at full graphs. For full graphs, vice versa, we know that they always possess 1. So like the example that we saw on the previous slide, that full graph. And one more example when we know for a fact that a graph does not possess a Hamiltonian cycle is if one node only has an out degree or an in degree of 1, so one outgoing edge, then this graph can also not possess a Hamiltonian cycle, and this was the first example that we saw in this video. Lastly, we can ask the question, how many such cycles exist? And here, once again, the answer is this is not very trivial, but for certain classes of graphs, we can come up with a rule. Obviously, if none exists, if one of those cases applies, we can immediately say it's 0. Vice versa, for full graphs, we know that the number of Hamiltonian cycles is n minus 1 factorial divided by 2, assuming that the starting point and the direction are relevant, so, or predetermined. So for example, if we say we always start at the entrance and then we move forward, and it doesn't matter if we move in this direction or in this direction on exactly the same route, then we have n minus 1 factorial divided by 2. And this is also something that will help you for the example on the previous slide to determine all Hamiltonian cycles, because of course also there, the number that you can come up with should be n minus 1 factorial divided by 2. What I would like you to take away from this web lecture is first of all what a Hamiltonian cycle is, so the definition. Secondly, I would like you to remember when such Hamiltonian cycles exist and when they don't. And what I would like you to do following this web lecture is first of all listing all cycles for both examples that we saw on previous slides. And what we're going to look into in 3 follow-up videos is the traveling salesperson problem, which utilizes the concept of Hamiltonian cycles. Thank you very much.